Thank you, Christian. And that's exactly what I want to do. I am the field technical expert, so I'm the field engineer for Chevron, working with turbines and turbine oils. And I've got about almost 20 years with Chevron working in this industry. Over that time, I've done quite a number of varnish cleaning approaches, actually on-hand, first-hand service appointments with turbines to clean out varnish problems, and I'd like to share some of those with you today. So this is real-world first-hand examples. It doesn't demonstrate all examples in the world, but it should give you some ideas of some of the of tailoring successes and compromises with different tools and different approaches available. We've got 5 case studies to talk about here that does envelop a few more than just 5 turbines, and I'll explain those as we go along. I'm going to focus on removing varnish, not necessarily prevention, but removing. So you have a problem, you're trying to get rid of it. We've got a variety of approaches and products, and I also have some information on bench test validation of some of those approaches and products as well at the end. So we'll jump right into the first one. This was done quite a number of years ago. GE7FA turbine. There were actually 8 of these turbines on the site. They were experiencing sticky valves. They were running a product, a Shell Turbo T product, had high MPC, and so we went in with an approach to use Du Bois Step 1 cleaner, which was commercially available at that time, and we had some experience with that. It's a calcium sulfonate detergent dispersant. And knowing the chemistry of that and turbine oils, that type of detergent dispersant is in the alkaline family, so it's not technically compatible with turbine oil. So the time frame that it can be left in a turbine oil is short, but it is an effective cleaner. So we shot for 2 days of cleaning as per the time requirement guide of the instructions of that manufacturer. And we also planned in quite a bit of rinse oil, because we know with that incompatibility, if a little bit of the cleaner is left behind, we have a major impact on the performance of the new oil. So we also had to calculate about 4,500 gallons there. Roughly, that's about $40,000 a turbine for this cleaning process. That doesn't include the final fill oil. So that's the service, that's the equipment that's provided, and that gives you kind of a price range on that type of turbine. But this was done a number of years ago as well. And that does include also manual reservoir cleaning, because an important part of a chemical cleaning or a turbine cleaning is entering confined space entry of the reservoir and getting all of the garbage that's out that has fallen to the bottom of the reservoir, and we'll talk about that. The other key point is draining all of the old oil and cleaner out. Folks have often asked, do I have to use a rinse oil? That depends on the compatibility of your cleaner, but also how thoroughly you can drain the system. On a 7FA, there's about 14 individual drain points to get all of the oil out of the system, and the target is to get 95% or better of the oil, the old oil and the cleaner out of the system, and then rinse it through to get the remainder out. So this is kind of what the oil looks like in the process. The old oil looked pretty nasty to start with. We add the cleaner that pulls varnish off of the surfaces into the oil, so it looks even worse. Then we put in a rinse oil. You can tell that went in water white and clear, so it does pick up some extra debris that was left in that did not get drained out, and then we have the fresh oil that goes in. This is after the cleaning. As you can see on the left, we have a rag that has been in there for a number of years. We have settled varnish that was a number of years. This example on the right was very extreme. This pump had failed and had been allowed to run in a failed condition for a number of months. So it essentially cooked the oil in that reservoir, and that black hard deposit you see on the bottom was very tenacious, and it was a result of cooking that oil over a number of months. And underneath the pump there, that deposit there was actually about 1.5 inches thick. So setting expectations around a chemical cleaning is important. That type of heavy deposit, something that's been cooked on very heavily, is probably not going to be affected by most chemical cleaners. There may be still some manual cleaning that's required to get some of those heavy deposits out. But in the end, we did clean the system and got a cleaner and eliminated the problem he was looking for. So although we had some compromises of having to use a flush, having to use some manual cleaning, we did get the system a lot cleaner than it was to start with, and they had a lot better performance with the new turbine oil that was put in afterwards. These are some other pictures of debris that were pulled out of the bottom of those reservoirs. As you can see, there's miscellaneous parts sometimes. That's always kind of a point of curiosity to see where it fell out of and if they still need it. but also heavy varnish that was mechanically scraped out of the reservoir even after the chemical cleaning was done. So after the cleaning, we did have less bathtub ring, but you can still see there is some bathtub ring there. We did get rid of the valve sticking issue, so cleaning through the valves, which was their primary concern, we did accomplish. They went to an upgraded oil, and it's been in operation for about 10 years since then, and they did improve on the performance of the system by cleaning out the system and preparing the system for performance of the new oil going in. So we have another case study. This is also a GE7FA, and this is actually some experience that was gained over 2 sites that include 5 different turbines. All 4 of the combustion turbines were 7FAs, plus we had a D11 steam turbine thrown in there. In this case, the oil condition was acceptable at the beginning of their process, so they didn't really want to drain the oil out. They just had some sticky valves. So they chose to use an oil-soluble PAG, the EcoSafe Revive product, to gain some life out of the oil, to extend the life of the oil and get some time out of it. So that was what their primary goal was, is to not do an oil change now, but to wait a while before they did the oil change. I was brought in after they had run for a number of years with that oil-soluble PAG in the system because they saw some deposits in there. So what we saw when we drained the oil out was that this oil-soluble PAG did not stay long-term dissolved in the mineral oil. In this case, there's 2 different locations. One of the locations was using a Conoco turbine oil product. The other one was using a mobile turbine oil product. In both cases, we saw separation between the PAG into a 2-phase solution, where the PAG is in the darker solution and the mineral oil was in the lighter solution. You can see that here in the bottom of the reservoir, here in the bottom of a pail as we were draining it out, and even in some that were draining across a rag here. This 2-phase separation also left quite a bit of deposits in the reservoir. So this looks pretty bad, but keep in mind that each of these 2 locations got what they were looking for. They did extend the life of the oil, or at least the operation of the turbine, for a couple of years, 2 to 3 years typically. What they didn't expect is to have to do a fairly thorough cleaning afterwards. So on one of these locations, we did only a manual cleaning. On the other location, we went in with a Du Bois Step 1, again, there to clean out as best we could the deposits in the system. The picture on the right here is the deposits that were remaining even after that Du Bois Step 1 was used. And we did some lab testing ahead of time to see if that was going to be effective at removing these deposits. And it was, in the lab testing, effective at removing some of the softer deposits. And those deposits did show some evidence of both the mineral oil degradation byproducts and also the PAG degradation byproducts. So that was, those deposits are a chemical mix of both. So they did get a positive result. They got a couple of years of reduced valve sticking, so that was good. The PAG is very highly polar, so it does tend to keep deposits in the oil for a period of time. But our conclusion from what we saw is that they probably tried to extend the life a little bit longer than was practical, at least with the oil condition and the operating conditions that it was in. We did see quite a bit of filter plugging increased after that 2 to 3 year period, both on the CTs and the steam turbine units. And so I think the steam turbine was the most severe. They were having to change the filters every couple of weeks to keep that unit in operation. They required manual cleaning to get rid of those heavy deposits. And we did see both mineral and PAG parts from that. On case study 3, this was a GE7EA, yet a different approach to it. Their oil condition was very good. This one happened to be running Chevron GST. They had some sticking of the torque converter startup servo valve. And this was an area that has very low flow and is only used when the turbine started up. They had a fairly low varnish potential between 15 and 25, depending on when the samples was taken. The oil condition was good at 60% RPVOT, and they did not want to change the oil, again, in this case. So what we started with was basically 2 different phases of this. We first installed a varnish removal filtration technology, a resin type of varnish removal filtration. And we watched the MPC drop from 25 range down to about 10 range. But we did not see that the sticky valve got any better. It was still sticking and causing some problems on startup. because the oil itself is very stable. It's not designed to be an effective cleaner. So it wasn't going into that sticky valve and cleaning out the deposits that were existing in that sticky valve. And we did do some testing. We saw that the filtration did affect the rust inhibitors. It depleted the rust inhibitors, which was expected with that type of filtration technology. So we went back after that and we added in a synthetic solvency enhancer, which is alkylated naphthalene. In this case, it was King Industries product. And the oil got quite a bit darker, but the MPC actually lightened up some. So that did show some evidence to us that we were pulling some varnish off the surfaces, but that varnish was staying dissolved in the oil as a solvency enhancer is supposed to do. So we did pull that off of the valve apparently because the sticky valve issues ceased with their problems. So we did have the right impact on that. And we continue to run with this very light treat rate of alkylated naphthalene and also the varnish removal filtration technology for, I believe, 6 years after that, 6 or 7 years without any other operational concerns. So we were able to physically clean or to chemically clean the problem and fix the problem without changing the oil. So this was an approach that worked for them. We have done subsequent testing in the lab, and I'll talk a little bit about that, about alkylated naphthalene as a cleaner. And it's not a very effective cleaner necessarily as far as cleaning up heavy deposits, but it is pretty compatible. So it is a viable approach to something where the oil is not ready to be changed. Next case study I want to talk about was a Solar Taurus 60. This is actually at a Chevron site. It's a fairly small sump. We had heavy varnish deposits in the fin fan coolers, the oil cooler up front of this. So the temperatures were extremely high. They were within 1 degree of trip temperature when they were running, so they had to derate the unit to manage the temperatures of the oil to keep the turbine running. There's 2 of them side by side there. And that was about 6 months out of each year they had to derate that turbine. That's quite a loss of revenue because we were selling the power back to the utility grid. And so it was a significant decrease in the output of the turbine. So in this case, what we chose to do is based on experience that I had had and that we had had in the industry in cleaning chemicals and the compromises of compatibility of a lot of those types of chemicals, I had challenged Chevron to see if we could come up with something better. So this was a field trial product that we have since introduced, which is a Chevron specific cleaner. And so we installed this new cleaner, Chevron Vartec Industrial System Cleaner, to see if we could correct that deration problem. Within about 15 minutes of installing the cleaner, we watched the header temperatures drop and the bearing temperatures drop fairly significantly. So we used that as our indicator of whether we had proof of performance, proof that we were doing something, that we were being effective. And clearly we were. So we got the temperatures down, and we were planning on leaving it in there for a couple of weeks. The very next day after we put it in, we stopped derating the turbine. We ran it up to full output with no temperature alarms, no temperature trips. Everything worked really well. So we really felt that was good, measurable, objective evidence that we were effective at cleaning the deposits. We also took pictures of the reservoir both before and after we put the cleaner in. We did see reduced bathtub ring, but there is still some bathtub ring remaining. Again, setting the expectations that a chemical cleaning process doesn't get out every last bit of deposits. It depends on what's there to start with and how long you leave the chemical in and how effective that cleaner is. In this case, we did see some increase in filter differential pressure. That was something we were concerned about. As you pull varnish off surfaces, sometimes that will deposit in the filters. We did see that stabilize below the alarm point, and it actually started dropping back off as the varnish that was in the filters continued to stabilize into the oil. Since this unit had duplex filters on it, we let it run that way for the 2 weeks. We never saw a further increase in that, and so we were comfortable with the way this operated. If you have a system without duplex filters, then it may be worthwhile to go ahead and change that filter. We had another site that we did that, and after we changed the filter once, delta P stayed good and low. So that was a case where we clearly measured whether we had the desired impact. We have another case study that was also a a Chevron rig. This is an offshore platform where we have 3 turbines running. These are larger Solar turbines. Similar situation where the varnish, where the oil coolers were varnishing up and reducing in effectiveness. They weren't having to derate, but they were having to swap those coolers out to send them out for mechanical cleaning. And they had to do that about every 4 months. So the varnish was building up fairly quickly in those coolers. In this case, they were plate type coolers using seawater for cooling. So we went there, we set up a cleaning schedule, basic process. We did install a kidney loop filter because it's a very highly critical application and a long ways from home. We went up to about 14% Vartec because we had extremely heavy varnish in the reservoirs. We ran it only for 2 days because we wanted to compare this process with a process identically that we had done a couple of years before using a calcium sulfonate detergent dispersant. And then we drained and we did a rinse, basically because we had the oil there. We wanted to make sure we got all the old oil out of there. We did a fairly thorough drain, but we still rinsed the heel out of the bottom of the reservoir because on this turbine, it's impossible to get inside the reservoir and mechanically clean or squeegee out the oil. And then we filled with new oil. The results that we saw here, also we were measuring temperature across that cooler. And we saw that when we got to about 5% concentration, we really started to see that temperature drop, that header temperature drop. And so when it came down to the level where the thermostat was finally controlling temperature instead of ambient conditions controlling temperature, that's where that temperature leveled off. And we left it in. That happened within about an hour period of time. So we had a good, positive, measurable result within about an hour period of time. We left it in there for about 2 days and to try to help clean some of the heavy stuff in the reservoir. Also, we wanted to do be very conservative about that. Some interesting things we saw on this site. We saw no increase in filter differential pressure. And we also see the MPC, which was very high at about a 50. As soon as we put the cleaner in, that MPC went from 50 to 1, showing that the cleaner was effectively stabilizing the oil or the varnish in the oil, so it was not coming back out on the patch when we did the MPC patch test. We do see some debris in the filter, so we analyzed that quite well. Delta P stayed nice and low, so we were very confident that way. When we had done this with the calcium sulfonate before, we had seen severe filter plugging. It happened about every 10 minutes they were having to swap out filters. So this was a vast improvement over the chemistry we had chosen to use on this exact same unit 2 years prior. This is the testing we did to validate, make sure we didn't have any loss of water separability, RPVOT, and we watched MPC as well when we were doing this with the later samples that we put in as well to make sure we hadn't left any contamination in. I want to touch base a little bit on some bench testing of the comparison of cleaners, since we had some very vast field experience with cleaners, but that's somewhat subjective because each case that you go into is a little bit different as far as the oil it's going into and the conditions that it's going into. So what we had done as part of the development of this new cleaner is to start with beaker testing, which you see there at the bottom. And then we actually built a flow rig that's been written up in TLT and was actually presented at STLE back when we could meet face-to-face. So we could actually video the cleaning of varnish coupons. So first we had to invent a process to varnish a coupon, and that varnish is representative of turbine oil varnish. So it's not representative of all varnishes, and we've heard from Dr. Wooten in the past that there's a lot of different chemical species of varnish. We came up with one that was consistent, that was representative of R&O oil. And we tested a lot of different cleaners, both for effectiveness and also for compatibility, so that we could make sure that we had something that was both effective and compatible to improve on some of the things we had seen in the past. These are some of the results that we saw. I'm not publishing the names of the competitors because this is just our testing. There's no ASTM standardized around this. We've tried to come up with some that works fairly well so that we could compare the results. And so we saw very good effectiveness with the new product that we had come up with, which was quite good. And we saw a number of products, and I think in total we looked at over 20 products. There were a number of products that in that circulating rig, they just didn't remove any of the varnish off the coupon. And so we didn't bother testing them any further for compatibility or whatnot. We kind of set them aside saying, well, those aren't really effective. And that's in the family where the alkylated naphthalene cleaners tended to fit. We tested straight alkylated naphthalene and some that were kind of based on that. And they just were not strong cleaners. They are very compatible, but not very effective. And so that's where those fit into. We also took a look at the time to see if, the speed of a cleaner, and there were some other cleaners that were a little bit faster, but not as thorough. So we got some indication of that time is a critical parameter to take a look at that way. And we also took a look at the characteristics of how they pulled varnish off of surfaces, because what we really want is very small, stabilized varnish in the oil, either dissolved or dispersed in the oil, such that it won't stick into valves, it won't stick into filters, it won't cause any other issues. We saw some of the others that were kind of coming off in globs, and one of them that just kind of moved the varnish from one place to another on the coupon. So that gave us some idea of characteristics of the different types of chemistries that are used in cleaners. We also took a look at the filter that we had in that circulating rig to see the size of the particles that were caught in that filter. And we also saw differentiation here as far as the size of varnish particles that are brought off the surfaces. Again, our desire was to have it come off layer by layer without coming off in chunks by chunks. And it seems like we accomplished that fairly well in comparison with some of the other chemistries that we took a look at. So when we are considering the chemistry of cleaners, I think it's important to have a lot of tools in your toolbox. I'm a mechanical engineer by nature, and I like to have a lot of tools available to me and to use those tools as they are best suited for the circumstances and the outcome that you're looking for. So I'm not discounting any of these chemicals and in any of these cleaning approaches. They just need to be tailored for the successes and the compromises for the circumstances that you're going into. And so this is kind of showing a little bit of that chart. And this again is focused on turbine oils. We talked about the alkaline nature of the calcium sulfonate detergent dispersions. They're not necessarily compatible with turbine oils, which are acidic, but they may be more compatible with like zinc containing hydraulic oil, which is in the alkaline family. So those are some things to consider as well as you get outside of this narrow scope that we looked at for turbines today. The other thing that is important with that incompatibility in some cases is when there is a poor compatibility with the oil, that time that you can leave the cleaner in the system varies quite a bit. So if you're incompatible with the oil, then you have a limit on how long that cleaner can stay in before it starts to perhaps cause worse problems than you're trying to solve. So with our new cleaner, we've shot for about 30 days. We have actually left it in 2 turbines for 6 months without degradation over that time, but it's not intended to be a top treat for extending the life of oil for a long period of time. It's intended, as we talked about to start with, as a cleaner to clean a system, preparing that system for new turbine oil to go in. There are some other chemistries that may be more appropriate for a long-term top treat to buy time until an oil change is needed. But this is kind of what we've seen, focused on cleaning out the systems. And also what we saw is the very, very heavy varnish that's in some systems that's been accumulated over 10 years. It took 10 years to put it there. It's going to take some time to get it out of there. So a short window of cleaning may not be enough time to get it out. So for this case study summary, again, this is my direct experience with a number of chemical cleaning approaches that we had. All of those approaches left some deposits to different extents, those deposits depending on the chemistry of the deposits, how heavy the deposits are, and what chemistry was used to remove them. Also, that depends on the removal effectiveness, depends on temperature and flow rates and some other things. That chemical compatibility really drives whether or not you need to flush out the chemicals, as does the completeness of the drain. People have asked me, all right, this new product is compatible with oils. Does that mean I can skip the flush? In some cases, that may be a possibility, depending on how completely you drain the system. If you leave 20% of the old oil and the cleaner in there, that's kind of a sloppy drain. and you probably ought to use a flush to rinse the rest of that out of there just to get a good charge of new oil in there. And it also comes down to a financial choice. If you are recognizing that leaving some garbage in there, not doing a flush, may have a compromise, and whether that's an extreme compromise or a slight compromise depends on the chemistry that you're using for cleaning. As long as you recognize that may give you some compromise, that may be a good compromise from a financial standpoint. If the unit's going to be mothballed in 3 years, who cares if the oil lasts for 10? The oil condition also can drive that approach. If the oil is ready for change, do a chemical cleaning and drop the oil out of there. If you don't want to change it, then there may be some other choices that way. And also the varnish filtration, and we've tested this with a number of the varnish filtration technologies. Those also have some compromises in oil performance. Some of them can remove the EP additives in EP type of turbine oil. That's typically phosphorus. They can remove rust inhibitors and foam inhibitors. Now, it may be that the benefit outweighs the cost. The benefit of getting rid of varnish outweighs the cost of the compromise in oil performance, but that is something that needs to be taken into consideration. So multiple tools make for a better toolbox, and so I wanted to share with you a little bit today some of the tools that we've used in the past and some of the successes and some of the compromises that they look for.